In question number 16, two light wires of length L and 3L, radius R and 2R, respectively are hung with a weight mgh shown. If Young's modulus of the both wire are y, then net elongation. Some elongation will be produced here in this wire and some would be here. Total elongation can be given as sum of the elongation produced in both the wire. So elongation, what we write here as F divided by area into Young's modulus into length should be taken as elongation for any single wire. Looking into the situation, I would say elongation, total elongation would be given as elongation in this wire. This is F would be equal to mg, area being pi r square, Young's modulus this much, length being L. Elongation in this wire is, this is the force, area being pi into r square. Look into the here value, the r is 2r, so it is 4 pi r square, Young's modulus, and length being 3L. Just arrange this answer. We shall have mgl by pi r square y. It will be 1 plus 3 by 4. That will be 7 by 4 altogether. So option 4 is the correct answer for question number 16. Now let's take on to question number 17. A uniformly tapering conical wire has radii at its two ends as r and 2r. Here it is r and here it is 2r respectively. Its length is L and Young's modulus is y. Find its elongation if it is pulled at both ends by force F. So the variation of radius along this direction would be, if I'm taking this part to be x is equal to 0, this part to be x is equal to L, I shall have at any distance, if this delta x, the original length and the radius being r, I'll write down r to be equal to, it is r by L x plus r, or it will be r x by L plus 1. This is the value of the radius here. So the elongation at this particular point, it is delta L will be, force is F, radius being pi r square, it is x by L plus 1 whole square, Young's modulus was this much, and the original length of this much of the part was dx. So integral of this portion would lead us to the total elongation. I would say total elongation to be delta L, it must be written as F dx divided by pi r square y, it is x by L plus 1 whole square. Integration of this portion would be F by pi r square y, L here it will be minus of 1 by x by L plus 1 from 0 to L, or this delta L would be FL divided by pi r square y. This portion will have the value of 1 by 2 here. So total elongation would be FL divided by 2 pi r square y. This is the final answer for the elongation. So option number 3 is the correct answer for question number 17. Now let's take on to the question number 18. Fractional compression minus delta V by V of water at depth of 4000 meter in the ocean is, given the bulk modulus of the water is 2.2 into 10 to the power 9 Newton per meter square and G to be taken as 10 meter per second square. Straight away, very simple question. We know by the stress strain relation itself, this would be taken as the stress strain this much would be minus a bulk modulus. We need to just find out the percentage change here. So minus delta V by V must be taken as delta P, change in pressure. It is rho GH. Well, rho is 1000, G to be taken as 10, S to be taken as 4000 meter. Divide by bulk modulus, it is 2.2 into 10 to the power 9 Newton per meter square. So 1, 2, 3, 4, 5, 6, 7. I will have here as divide by 2.2 into 100. So the percentage change would be minus delta V by V into 100 or it is 4 divided by 2.2%. How much is the answer? It will be 1.82%. So the option 4 is the correct answer for question number 18. Now let's take on to question number 19. Two immiscible liquids of density D1 and D2 are filled in a circular tube in a vertical plane. Each liquid occupy 1/4 of the circular tube and the radius joining their interface makes 37-degree angle with vertical. The ratio of D1 D2 is. What I would say, if I'm taking this to be the circular tube, this angle being 37 degree, this angle should also be 37 degree, and this should also be 37. Up to this much of the portion is being occupied by the liquid of density D1, and from here to here it's being occupied by the liquid of density D2. So if I compare the pressure at this point from both the sides so that the system would remain in equilibrium, perhaps I'll be getting the proper answer there. Well, writing down the pressure at this point from this way, this point being P0 here plus this being 53 degree, so this is the height. I would say rho, it is D1 G, this is the height here, it is R minus R cos 53. 1 cos 53 means it would be 3 by 5, must be equal to P0 here. This height, it is D2, this angle is 37, so it is R sin 37. Sin 37 is 3 by 5 plus D2 rho, it is G R. This is the height, it is 37 degree, so it is cos 37, 4 by 5 plus this density being D1 and this height, this is 37, it is R minus R cos 37, it is R 1 minus 4 by 5. This P0 will cancel out, it is D1 GR 2 by 5, here it is 4 by 5, 3 by 5, it will be 7 by 5 D2 GR plus 1 minus 4 by 5, it is 1 by 5, it is D1 GR by 5, or along this side I will have D1 GR by 5 equal to 7 by 5 D2 GR. So finally the option D1 by D2, D1 by D2 will be 7 by 1. Well, for question number 19, option 4, the ratio is 7:1 is the correct answer. Now let's take on to question number 20. In question number 20, a stone of relative density 2.5 is released from rest on the surface of lake. Ignoring viscous effect, the stone sinks in the water with an acceleration. We need to find out the acceleration taking into account the buoyancy forces. If the V0 was the volume and let's say rho naught is the density of water, then relative density being 2.5 into G, this is the total downward force. Force of buoyancy would be V0 rho naught into G divided by total mass is how much? It is V0 rho naught into 2.5. This will be the acceleration of the stone. 2.5 minus 1, it is 1.5 V0 rho naught G divided by 2.5 V0 into rho naught. This is acceleration, or acceleration is, this will cancel out, it is 3 by 5 into G. If I take the value of G to be 10, I will have this value as 6 meter per second square. Question number 20, option 1, acceleration is 6 meter per second square is the correct answer. Now let's take on to question number 21.